Welcome to the Deep Sleep Science Channel. Tonight, we're drifting into the quiet and ancient world of asteroids, small, silent travelers that have been circling the Sun since before Earth even became the planet we know today. These distant worlds may look like simple rocks from afar, but each one carries a story billions of years. Old stories of fire and formation, of collisions that shattered entire worlds, and of tiny forces so gentle they take millions of years to change a path through space. As you listen, you'll discover how some asteroids may hold the ingredients that helped life begin on Earth, how others are fragments of lost worlds, and how even sunlight itself can slowly move an asteroid across the solar system without making a sound. We'll move from the largest asteroid worlds to the smallest drifting fragments, from powerful impacts that shaped planets to the quiet, almost invisible forces that guide these bodies through the dark. So before you settle in, you might like to leave a soft like, subscribe, or share a thought in the comments, and then simply relax as we explore these ancient, quiet travelers, one gentle idea at a time. One of the most remarkable things about asteroids is that they are not new objects at all, but survivors from the birth of the solar system around 4.6 billion years ago. Long before Earth looked the way it does now, these small worlds were already forming, colliding, and settling into their paths around the Sun. In that way, each asteroid is like a preserved fragment of a much older age, still carrying traces of the conditions that existed when planets were only beginning to take shape. Some asteroids have a beauty that is easy to miss at first, because through early telescopes they looked only like tiny points of light. That is where the word asteroid comes from, meaning star-like. They were not called that because they are stars, of course, but because they appeared as small pinpoints rather than visible round worlds. It is a gentle reminder that even objects that seem simple and distant at first can turn out to have rich and detailed stories hidden within them. When people imagine the asteroid belt, they often picture a crowded and chaotic place where rocks are packed tightly together. In reality, the main asteroid belt is vast and spacious, with enormous distances between sizable objects. Even though millions of bodies orbit there, most of the region is mostly empty space. So the asteroid belt is less like a dangerous field of obstacles and more like a wide and quiet zone where scattered remnants move around the Sun with great patience. Ceres is especially striking because it was the first asteroid ever discovered back in 1801, and scientists later learned it was important enough to be reclassified as a dwarf planet. That change in label did not make it less connected to asteroid science. Instead, it showed that the solar system does not always fit into neat boxes, and that some bodies stand at the edge between familiar categories. Ceres remains one of the key objects for understanding what the asteroid region is really like. Vesta is one of the most fascinating asteroids because it is large enough to have gone through a kind of internal evolution, more often associated with planets. Evidence suggests that it once became hot enough for heavy material to sink inward and lighter material to rise, giving it layered structure. That means Vesta is not just a simple rock drifting in space. It is more like a small surviving world that remembers an early stage of planet building. Some of the most dramatic events in asteroid science happened at Vesta's south pole, where enormous impact basins reshaped the body on a global scale. These impacts were so powerful that they blasted great quantities of material into space, and some of those fragments later became members of the Vesta family of smaller asteroids. In a quiet way, this tells a huge story. A single violent event on one asteroid could create an entire group of related bodies that continue circling the Sun long afterward. The asteroid named Psyche has drawn so much attention because it may help reveal what the metallic interior of an early planet-building body might look like. Some scientists think Psyche could be related to the exposed core of a disrupted protoplanet, though that idea is still under study. Even if the full explanation turns out to be more complicated, Psyche is still one of the best chances humanity has to study metal-rich planetary material without having to dig deep inside a full-sized ET world. Among the stranger asteroid shapes known so far is Cleopatra, which looks so unusual that it is often described as dog-bone-shaped. Rather than being round or even roughly potato-like, it seems stretched and oddly structured, with two small moons orbiting it. Its form suggests a complicated past involving collisions and reaccumulation, showing that asteroids can end up looking far more inventive and irregular than the neat spheres we often imagine in space. Some asteroids do not travel alone. Ida became especially famous because it was the first asteroid found to have a moon, a small companion called Dactyl. That discovery changed the way people thought about these bodies, because it showed that even small objects in space can have their own tiny systems. Since then, scientists have found binary and even triple asteroid systems, which means that miniature versions of orbital relationships exist even among these small remnants of solar system history. Didymos and Dimorphos became widely known because they formed the target system for NASA DART mission, the first real test of changing an asteroid's motion by direct impact. Dimorphos, the smaller body, orbited Didymos in under 12 hours before the mission. Then a spacecraft deliberately struck it, and the orbit changed measurably. It was an extraordinary demonstration that planetary defense can move from theory into action, using precision and patience rather than dramatic destruction. What made the DART result even more interesting was that the impact did more than just nudge the asteroid with the force of the spacecraft itself. Material blasted outward from the collision added extra momentum, almost like a natural recoil effect in reverse. That meant the change in orbit was larger than the minimum scientists had hoped to achieve. It revealed that asteroid deflection is not only about hitting a target, but also about understanding how its surface and structure respond. The European mission Hera is now heading toward the Didymos-Dimorphos system to study what happened in much finer detail. Rather than just confirming that the impact worked, Hera is designed to examine the crater, measure masses, study the internal structure, and help scientists understand exactly how the deflection changed the system. In that sense, DART was the first move, and Hera is the careful follow-up that turns a dramatic event into deep scientific understanding. Another captivating asteroid is Bennu, partly because it is active in a way many people would not expect from such a small object. NASA OSIRIS-REx mission found that Bennu sometimes ejects tiny particles into space. That means this small asteroid is not just sitting silently in orbit. It is dynamic, changing, and in motion on a fine scale, reminding scientists that even very small worlds can behave in surprisingly lively ways. Bennu also has a shape that seems almost sculpted by its own spin. It has a kind of spinning top form, with a raised equatorial bulge that likely formed as loose material slowly moved around under the influence of rotation and weak gravity. That shape is important because it suggests that the outer surface of a rubble pile asteroid can be rearranged over time, with stones and dust gradually shifting into new patterns. Ryugu, studied by Japan's Hayabusa 2 mission, showed a similar top-like shape and an unexpectedly rough, blocky surface. Before these close-up missions, many researchers expected more areas of fine dust. Instead, Ryugu revealed a rugged landscape full of boulders and uneven terrain. It helped show that small asteroids can be harsher and more angular than earlier models suggested, and that spacecraft missions often discover realities more complex than predictions. Hayabusa 2 did something especially impressive when it not only collected material from Ryugu's surface, but also created an artificial crater to expose deeper material and then sampled that as well. This was important because the surface of an asteroid is altered over time by sunlight, impacts, and space weathering. Material from below the surface can preserve a fresher record of the asteroid's original nature, offering a more direct window into ancient solar system chemistry. OSIRIS-REx achieved another major step when it collected a sample from Bennu and returned it to Earth in 2023. That sample gave scientists controlled access to primitive asteroid material without depending only on meteorites that had fallen through Earth's atmosphere. Early studies found carbon and signs of water-bearing minerals, reinforcing the idea that some asteroids preserve ingredients linked to the earliest chemistry of the solar system. Itokawa became a landmark in asteroid science because it helped establish the idea that some asteroids are rubble piles, meaning they are made of many fragments held together mostly by gravity rather than being one D&D. Solid, monolithic rock. Its surface showed both rough areas and smoother, low regions with fine material gathered there. This made Itokawa feel less like a single carved stone and more like a loosely assembled small world with its own shifting surface processes. Eros was another turning point, because the Near Shoemaker mission became the first spacecraft to orbit an asteroid and later make a controlled descent onto one. Eros showed that a near-Earth asteroid could have an elongated shape, a heavily cratered surface, and even ponds of finer material in some regions. It helped transform asteroids from distant light points into places with texture, structure, and local variation. One of the most powerful ideas in asteroid science is that a body as small as Vesta can preserve a crust, mantle, and iron core, much like a simplified version of a terrestrial planet. This shows that the line between asteroid and planet-like object is not as sharp as it may seem. Some asteroids are not just leftovers. They are partly developed worlds whose growth stopped before they could become full planets. Ceres offers a different kind of wonder because, unlike dry and rocky Vesta, it is rich in water-related minerals and occupies a transition zone between rocky and icy bodies. It suggests that the asteroid region is not made of one simple kind of object. Instead, it contains a spectrum of worlds, some closer in character to rocky planets, and others hinting at the chemistry of colder, more distant regions. Jupiter's Trojan asteroids are especially awe-filled because they share Jupiter's orbit around the Sun while clustering in stable regions ahead of and behind the giant planet. These groups, often called the Greek camp and the Trojan camp, may preserve primitive material from very early in solar system history. Their stability has allowed them to remain in place for immense spans of time, almost like quiet archives traveling in step with a planet. The Lucy mission is remarkable because it is the first mission dedicated to exploring Jupiter's Trojan asteroids. By visiting several targets, including binary systems, it gives scientists the chance to compare a whole collection of ancient small worlds rather than relying on just one example. This broader approach may reveal how varied these bodies are and what they can teach us about where material formed in the young solar system. Asteroids are often called minor planets, and that name carries an important truth. They orbit the Sun just as planets do, but on a much smaller scale. The name reflects the fact that they are part of the same solar family of orbiting bodies, yet their histories are often even older and more fragile, preserving clues from a time before planets fully finished forming. Most known asteroids orbit the Sun in the main asteroid belt between Mars and Jupiter. This broad region serves as the best-known home of asteroid populations, and it acts as a kind of historical storehouse for fragments, survivors, and partially evolved small worlds. While not every asteroid stays there, the main belt remains the central region for understanding the larger asteroid population as a whole. After Ceres was discovered, Vesta, Pallas, and Juno followed fairly soon after, and together they helped overturn the old expectation that there might be one single missing planet between Mars and Jupiter. Instead, astronomers realized that the region contained many bodies. That shift in understanding was important because it changed the story from one absent planet to a whole population of smaller worlds. Large asteroids can preserve evidence of early solar system heating, melting, and internal separation into layers. In other words, they can act as records of major physical processes that happened very early in planetary history. By studying them, scientists can explore how heat moved through young bodies, how metals and rock separated, and how some worlds began to organize themselves internally. Smaller asteroids often preserve more primitive material that has changed little since the solar system formed. These bodies may not have been heated enough to melt or differentiate, so they can retain ancient minerals and compounds in a more original state. That makes them deeply valuable to science, because they may preserve a simpler chemical memory of the early solar system. C-type asteroids are the most common broad class, and they tend to be dark, carbon-rich, and ancient in character. Because they are rich in primitive material, they are especially useful for studying the early solar system's chemistry. Their low reflectivity also reminds astronomers that an asteroid's appearance can be misleading, since very dark objects can be large without looking especially bright in the sky. S-type asteroids are generally stonier and contain silicate minerals mixed with nickel-iron metal. This makes them different from the darker carbon-rich types and gives them a somewhat brighter, more reflective character. They help scientists understand the range of rocky materials present among asteroid populations and how different parent bodies evolved under different thermal conditions. M-type asteroids are associated with metal-rich compositions, though that does not always mean they are just bare lumps of exposed metal. The class includes complexity, and scientists still need careful observations to determine what an individual object is truly made of. Even so, these asteroids are especially interesting because they may be linked to the metal-rich interiors of disrupted early worlds. Asteroids usually have no atmosphere, which means their surfaces are directly exposed to sunlight, the vacuum of space, and repeated impacts. Without air, weather, or clouds, the surface experiences space in a raw and immediate way. This makes asteroids especially useful for studying how airless bodies change over time under the direct influence of radiation and collisions. Because asteroids lack atmospheres, marks on their surfaces are not erased by wind or rain the way they would be on Earth. A footprint, a landing trace, or an impact scar can remain for extremely long periods if later events do not disturb it. This helps explain why asteroid surfaces can preserve ancient evidence so well, even after vast stretches of time. Kirkwood gaps are regions in the main asteroid belt where fewer asteroids are found because orbital resonances with Jupiter gradually destabilize those locations. These gaps are not empty by accident. They are shaped by the steady gravitational influence of the solar system's largest planet. Over long periods, Jupiter effectively clears certain orbital rhythms from the belt. An asteroid in a 3-to-1 resonance with Jupiter goes around the Sun 3 times for every 1 orbit of Jupiter. That repeating pattern may sound simple, but over long times it can create powerful gravitational effects. These resonances help shape the structure of the asteroid belt and can slowly push objects into new paths. Some asteroids drift through space because of the Yarkovsky effect, a very small force produced when an asteroid absorbs sunlight and later re-radiates that energy as heat. The force is tiny, but over immense stretches of time, it can gradually shift an orbit. It is one of the beautiful examples in astronomy where something subtle and almost invisible can still reshape the larger picture. The Yorp effect is another delicate process, and it can slowly change an asteroid's rotation rate or even tilt its spin axis over time. Sunlight does not just warm these small bodies. Under the right circumstances, it can gently alter the way they spin. This means that even light itself can participate in the long-term shaping of asteroid behavior. Those thermal effects matter because they can slowly move asteroids into resonances that then send them inward toward the inner solar system. So a tiny force caused by heat can become the beginning of a much larger orbital journey. This is one reason asteroid science often depends on understanding both dramatic collisions and very slow, quiet influences. Near-Earth asteroids are asteroids whose orbits bring them relatively close to Earth's orbit. That does not mean they are all dangerous, but it does mean they are especially important to track and understand. These are the bodies most relevant to both planetary defense and future exploration, because their paths cross the neighborhood of the inner planets. Near-Earth asteroids are divided into groups such as Asteroids, Artens, Apollos, and Amars, based on the details of their orbital geometry. These categories help astronomers organize a large and varied population. Instead of treating all near-Earth objects as one kind of thing, scientists sort them by how their orbits relate to Earth's path around the Sun. Asteroid asteroids orbit almost entirely inside Earth's orbit. That gives them a distinctive place among near-Earth objects, because they spend their time closer to the Sun than Earth does. They are harder to observe in many cases, which makes them an interesting and somewhat challenging group to study. Aten asteroids have semi-major axes smaller than Earth's, but they can still cross Earth's orbital path. That means their average orbital size is smaller, yet their motion still brings them into Earth's neighborhood. Their classification helps show that orbital patterns are subtle, and that closeness to Earth is not defined by one simple measure alone. Apollo asteroids have semi-major axes larger than Earth's and are among the best-known Earth-crossing asteroids. Because their orbits extend beyond Earth's while still crossing its path, they are an important group in impact monitoring and near-Earth studies. Many of the most discussed objects in planetary defense belong to this broad category. Amar asteroids approach Earth's orbit from outside, but usually do not cross it. They are near neighbors rather than direct crossers in most cases. This makes them a useful reminder that not every near-Earth asteroid represents the same kind of orbital relationship, and that careful classification matters when assessing their behavior. An asteroid can move from the main belt into near-Earth space through repeated nudges from resonances and slow thermal drift. This means that near-Earth asteroids are not a separate population born close to Earth. Many of them likely began much farther out and were gradually delivered inward by the combined effects of gravity and sunlight. Some near-Earth asteroids are easier to reach with spacecraft than the Moon when measured by the energy needed for the trip. That may seem surprising, but orbital mechanics can make certain asteroid missions more accessible than people expect. This is one reason asteroids are so important not only scientifically, but also for future robotic exploration and perhaps even human activity in space. Many meteorites found on Earth are fragments of asteroids. When scientists study those meteorites in laboratories, they are often holding actual pieces of these small worlds. This connection between fallen stones on Earth and distant bodies in space gives asteroid science a rare kind of closeness, where celestial history can be examined directly by hand. Ordinary chondrite meteorites are linked to stony asteroid material, helping connect laboratory analysis with telescope observations and spacecraft missions. These meteorites are especially important because they are common and well-studied, allowing scientists to build a detailed bridge between physical samples on Earth and their probable parent bodies in space. Asteroids matter so much in science because they connect observations from telescopes, direct spacecraft exploration, and laboratory study of meteorites into one larger story. They are not just distant objects to look at. They are also physical records, measurable targets, and sources of actual material that help explain how the solar system began and how it changed over time. Some asteroids contain hydrated minerals, which show that water once interacted with rock on their parent bodies. This is important because it means at least some asteroids were not always dry and inert. Water-related chemistry took place in parts of the asteroid population long ago, leaving mineral evidence behind. Primitive asteroids can also preserve organic molecules, giving scientists a chance to study the kinds of chemistry that existed in the early solar system. These are not signs of life, but they are valuable clues about the raw ingredients that were present as planets formed. In that way, asteroids help tell part of the larger story of how complex chemistry entered young planetary systems. Asteroids range from tiny boulders to giant bodies hundreds of kilometers across. So even though the word asteroid may sound like one simple category, it actually covers an enormous range of sizes and histories. Some are little more than irregular fragments, while others are large enough to preserve traces of major internal and geological development. Together, these quiet bodies show that the solar system did not form in one clean and orderly step. It formed through sorting, heating, drifting, collision, survival, and endless small changes spread across vast time. And asteroids, in their scattered and patient way, still carry that memory through the dark. Ceres is the largest body in the main asteroid belt, and that gives it a special place in asteroid science. While many asteroids are irregular and relatively small, Ceres is large enough to stand apart as a world of its own. It is big enough to have experienced internal changes, and its size helps it preserve clues about both rocky and water-rich processes that smaller bodies may not record as clearly. When scientists study Ceres, they are looking at something that sits near the boundary between a typical asteroid and a more planet-like body. Pallas is unusual not simply because it is large, but because its orbit is strongly tilted compared with many other major asteroids. That tilt means it moves through space in a more slanted path, making it different from many of its neighbors in the belt. This unusual orbit suggests that Pallas has had a distinct dynamical history, and it reminds scientists that the asteroid belt is not just one flat and uniform ring of objects. Even among the largest members, there is real variety in how these worlds move. Hygiea is another major asteroid, and some studies suggest it may come closer to roundness than many smaller asteroids do. That matters because roundness is linked to whether an object's own gravity has begun to shape it into a more balanced form. Even if Hygiea is not as dominant or famous as Ceres or Vesta, it helps scientists understand where the transition begins between irregular rocky fragments and bodies whose gravity has enough influence to smooth them toward a more rounded shape. Together, Ceres and Vesta contain a surprisingly large share of the asteroid belt's total mass. That means the belt is not made of many equally important objects, but is instead dominated in part by a few larger bodies surrounded by countless smaller ones. This uneven distribution matters because it tells us something about how matter was gathered, scattered, and preserved in the early solar system. The biggest survivors still hold an outsized amount of the belt's material memory. Even with those major bodies included, the total mass of the asteroid belt is still far smaller than the mass of Earth's moon. This is one of the most important big-picture facts about the belt. People sometimes imagine it as containing enough material to form a planet, but in its current state, it does not. That low total mass suggests that the region either never gathered enough material to finish making a full planet, or that much of its original material was removed long ago. Some asteroids do not rotate smoothly around one stable axis, but instead tumble through space. A tumbling asteroid rotates in a more complicated way, almost as if it is wobbling while spinning. This behavior shows that asteroid motion is not always simple or clean. Impacts, internal structure, and past gravitational interactions can all leave a body in a more complex rotational state, and that makes each asteroid's motion part of its larger physical history. Tutatis became especially famous as a clear example of a tumbling asteroid with a complicated rotation. Its motion showed scientists that some asteroids do not behave like neat spinning tops at all. Instead, they can move in ways that reflect an untidy past, with rotation patterns shaped by collisions and long-term gravitational influences. Toutatis helped make asteroid rotation studies more important because it showed that spin states themselves carry historical information. Large rubble pile asteroids usually cannot spin much faster than about a couple of hours per rotation without beginning to shed material. This happens because loose collections of rock held together mostly by gravity can only tolerate so much spin before the outer material starts to drift outward. This spin limit is a useful clue for scientists. If a larger asteroid is rotating too quickly, it may mean it is stronger and more solid than expected, or that something unusual is happening in its internal structure. Very fast rotators are often interpreted as either smaller objects or bodies with stronger internal cohesion. In simple terms, if an asteroid spins very rapidly and still holds itself together, it probably has more strength than a loose rubble pile would. This helps scientists estimate physical structure from a distance. By watching how quickly an asteroid rotates, they can begin to guess whether it is a fragile pile of fragments or a more compact and coherent object. Some asteroids have tiny moons, and that tells us that even small bodies can create miniature systems of their own. Gravity does not stop being interesting just because the objects are small. If an asteroid has enough mass and the right history, it can hold onto a companion and form a binary or even more complex arrangement. These moons are extremely valuable because their motion helps scientists calculate the mass and density of the asteroid they orbit. Binary asteroids consist of two bodies orbiting around a shared center of mass. This is important because it shows that asteroid systems can have internal orbital relationships that resemble, in miniature, the larger dance of planets and moons. Binary systems give scientists a natural laboratory. By measuring how the two bodies move around one another, researchers can determine mass more directly than they often can for a solitary asteroid. Triple asteroid systems also exist, which shows that small body dynamics can become surprisingly elaborate. A system with three interacting bodies is more complex and often more revealing than a simple pair. These systems demonstrate that the asteroid population is not made only of isolated fragments drifting alone. Some of them are part of delicate gravitational arrangements that form through impacts, reaccumulation, and long-term orbital evolution. Planetary defense studies often focus on making small changes long in advance, rather than attempting dramatic action at the last moment. This is one of the most important large-scale ideas in asteroid hazard planning. If an asteroid's path can be adjusted even slightly many years before a possible encounter with Earth, that tiny change can grow into a large missed distance later. The science of defense is often more about timing and precision than force. The usual goal of asteroid deflection is not to destroy an asteroid, but simply to make it miss Earth. This is a calm and important idea because it changes the whole approach. Instead of imagining explosions and shattered debris, scientists often think in terms of gentle nudges delivered early enough to matter. A slight alteration in timing or orbital position can be enough to avoid a collision entirely, which makes deflection a problem of planning rather than drama. Breaking an asteroid apart could create multiple dangerous fragments, which is why many defense plans prefer careful nudges over violent disruption. A shattered body might still send hazardous material toward Earth, and in some cases, that could complicate the problem rather than solve it. This is why understanding an asteroid's structure is so important. A porous rubble pile and a solid metallic object would not respond the same way to any mitigation attempt. NASA Sentry System continually checks known asteroid orbits for possible future impacts with Earth. This ongoing work is one of the quiet foundations of planetary defense. The system takes observational data and refines predictions over time, looking far into the future for possible close approaches. It is a reminder that asteroid safety is not based on guesswork, but on continuous measurement, calculation, and repeated improvement of orbital knowledge. The Torino scale is a public communication scale that runs from 0 to 10 and is used to describe asteroid impact hazards in a way people can understand more easily. Instead of forcing the public to interpret raw probabilities and orbital uncertainties, the scale gives a simpler framework for explaining how concerning a given object really is. It helps translate technical risk into language that is more useful outside specialist circles. A Torino scale value can change as more observations improve an asteroid's orbit. This is important because early results are often uncertain. A newly found object may briefly seem more concerning simply because scientists do not yet know its path precisely enough. As more data come in, the orbit usually becomes clearer and the risk level often drops. So the scale reflects not only danger itself, but also the current state of knowledge. Most newly publicized asteroid risks eventually fall to 0 as more data are collected. That pattern is one of the most reassuring truths in asteroid monitoring. Early uncertainty can create temporary concern, but follow-up observations almost always refine the orbit enough to show that Earth is safe. This is not because scientists were wrong to notice the possibility in the first place, but because orbital prediction improves steadily as more measurements are added. Asteroid 2024 POIR 4 briefly reached Torino Scale 3 before later observations removed the 2032 impact concern. This is a good example of how risk communication works in real time. At first, limited information allowed a non-zero concern to appear, but as the observational arc improved, the hazard was retired. Cases like this show why continued observation matters so much, and why temporary concern does not usually mean lasting danger. Some asteroid families are groups of fragments that came from one larger parent body, broken apart by impact. These families are important because they let scientists reconstruct ancient collisions in the asteroid belt. If many objects share similar orbital characteristics and related compositions, they may all be descendants of one larger body that was shattered long ago. In that sense, families are like debris fields that still remember the shape of a vanished past. Family members can often be identified because they share similar orbital elements. Their paths around the Sun are not identical, but they are similar enough to suggest a common origin. By comparing these orbital groupings, scientists can recognize which asteroids are likely relatives rather than unrelated neighbors. This allows the belt to be read not just as a collection of individual objects, but as the product of repeated breakups and reassembly. Young asteroid families can sometimes be dated by measuring how widely their members have spread over time. After a breakup, the fragments do not remain clustered forever. Slow processes gradually shift their orbits, spreading them apart. By studying how far that spreading has gone, scientists can estimate how long ago the original disruption happened. This turns orbital structure into a kind of clock. The Karen family is a good example of a relatively young asteroid family that helps scientists study collisional evolution. Because it formed more recently than many older families, its members have not had as much time to disperse. That makes it easier to trace them back to a common event. In this way, the Karen family helps researchers understand what happens after a body breaks apart and how asteroid groups evolve across time. Family ages can be estimated partly through the Yarkovsky effect, which slowly spreads asteroid fragments outward in orbit over long periods. This is a beautiful example of how very small forces can become useful scientific tools. A faint thermal drift acting over millions of years can help reveal when a family was born. So something subtle enough to seem almost invisible can still become part of a deep time measurement. Not every cluster of asteroids in orbital space is a true family. Sometimes objects only appear related until their composition is checked more carefully. This is an important caution in asteroid science. Similar orbits alone are not always enough to prove a shared origin. Scientists have to combine motion, spectra, and other evidence before deciding whether a group of objects is truly a collisional family or simply a temporary resemblance. An asteroid collision can be catastrophic enough to completely disrupt a parent body, or mild enough to leave behind a crater family without total destruction. This range of outcomes matters because the asteroid belt records both extremes. Some impacts erase the parent object as a single world, while others scar it and launch fragments without ending its existence. Understanding the difference helps scientists reconstruct the variety of events that shape the belt. Many small asteroids may not be untouched primordial bodies at all, but reaccumulated fragments from larger disruptions. In other words, what looks like one small asteroid may actually be a second-generation or even later-generation body built from the remains of something older. This changes the meaning of the asteroid belt. It is not only a museum of original survivors, but also a region full of recycled worlds. A rubble pile asteroid is made of many pieces held together mostly by gravity rather than solid rock strength. This means it can contain gaps, weak zones, and a loose internal arrangement rather than being one continuous block. Rubble piles are especially important because they behave differently during impacts, spin changes, and spacecraft interactions. Their structure can be surprisingly fragile, even when the overall object looks solid from far away. Rubble pile asteroids can have internal voids and uneven density distributions. That means the inside may not be uniform at all. Some regions may be packed more tightly, while others are more open or loosely arranged. This internal irregularity makes asteroid physics more complicated, because how a body responds to force depends not just on its outer shape, but also on the hidden arrangement of material inside. Bennu appears to have a less dense interior region, showing that a small asteroid can be internally heterogeneous rather than neatly uniform. This matters because it gives direct evidence that asteroid interiors can vary from place to place. Instead of imagining a simple object made of the same material throughout, scientists now know that some asteroids are patchwork structures with important internal differences. Low gravity on a small asteroid means a pebble tossed upward could travel a very long way before falling back, if it returns at all. This is one of the easiest ways to understand just how different these worlds are from Earth. A tiny push that would mean almost nothing here could have large effects there. The weakness of asteroid gravity shapes everything from surface movement to lander design to the outcome of impacts. Escape velocities on small asteroids can be only a few tens of centimeters or meters per second. That is astonishingly low compared with planets. On Earth, throwing something into space is impossible by hand. But on a tiny asteroid, very gentle motion might be enough to let material escape completely. This helps explain why impacts can remove debris so easily, and why asteroid surfaces are constantly vulnerable to loss and rearrangement. That weak gravity makes spacecraft navigation around asteroids much more delicate than navigation around planets. A spacecraft cannot simply behave as if it is orbiting a large, predictable body. Small changes, weak gravitational pull, and even sunlight can matter more than expected. Missions to asteroids, therefore, demand careful planning and constant adjustment, because the environment is subtle rather than forceful. Instead of behaving like aircraft landing on a solid world, asteroid landers often need to hop, bounce, or anchor very carefully, because touchdown speeds must be extremely low. On such a weakly gravitational body, a normal landing could easily turn into a rebound back into space. This means the simple act of touching the surface becomes a highly specialized engineering problem. Artificial impacts are especially useful in asteroid science because they expose subsurface material that has not been altered as much by sunlight and space weathering. The outermost layer of an asteroid has usually been changed by long exposure to the space environment. By opening a crater on purpose, scientists can access fresher material from below and compare ancient interior matter with the more weathered surface. The crater created on Ryugu exposed deeper material that could then be sampled. This was valuable because it gave scientists a chance to compare surface material with matter from underneath. The difference between those layers helps reveal how much change happens over time on an exposed asteroid surface, and how much older chemistry may still be preserved within. Subsurface samples are especially valuable because they allow scientists to compare fresh material with weathered material from the same asteroid. That comparison is powerful. It helps researchers separate what the asteroid was like originally from what happened later because of solar radiation, impacts, and other space processes. In this way, deeper samples improve the accuracy of asteroid history. Asteroids can contain metal, silicate rock, carbon compounds, sulfides, hydrated minerals, and other combinations of material. This wide range of composition is one reason asteroid science is so rich. The category is not made up of one simple kind of object. Instead, asteroids preserve multiple chemical histories, and their diversity reflects the many conditions under which solar system material formed and changed. Some metal-rich asteroids may preserve matter related to the cores of disrupted protoplanets. If this idea is correct in particular cases, then such asteroids are not merely rocky leftovers, but deeply buried material exposed by ancient destruction. That would make them extremely important, because they could offer a rare look at the inner metallic regions of early worlds that were broken apart before becoming full planets. Other asteroids never became hot enough to melt, and instead stayed chemically primitive. These bodies may still preserve minerals and compounds close to their original state. That makes them valuable for a different reason than differentiated asteroids like Vesta. Rather than showing internal evolution, they preserve the more untouched ingredients of early solar system matter. Short-lived radioactive isotopes in the early solar system helped heat some parent bodies from the inside. This heating happened because those unstable atoms released energy as they decayed. In the earliest millions of years, that energy could be enough to warm and transform small worlds from within. So the history of an asteroid can depend partly on whether it formed early enough to trap that internal heat. If an early asteroid became hot enough, metal could sink inward, while lighter rock rose outward, creating internal layering. This is the process known as differentiation, and it is a major step in the development of a planet-like structure. It turns a mixed body into one with distinct internal regions. Some asteroids preserve evidence that this happened, while others remain too cool for it to begin. Spacecraft images show that asteroid craters come in many forms, from fresh bowl-shaped pits to older, more subdued basins. This variety helps scientists read the age and history of surfaces. A sharp crater may be younger, while a softened one may have been altered by later events. Even on airless bodies, surfaces are not frozen in one perfect state forever. Time still leaves its mark. On low-gravity asteroids, crater ejecta can travel far or even escape into space entirely. This makes impacts on small bodies very different from impacts on planets. Instead of settling nearby, blasted material may spread widely or be lost. That affects how craters form, how surfaces are resurfaced, and how asteroid fragments can be launched into new orbits. Some asteroids preserve giant grooves or ridges connected to impacts or internal structure. These long surface features tell scientists that asteroid geology can be surprisingly dramatic. Even on a small body, stress from impacts can travel far and leave large-scale traces. A ridge or groove may therefore record not just a local event, but the way the whole asteroid responded as one interconnected structure. Asteroids can experience global reshaping after large impacts because shockwaves travel through such small bodies differently than through larger planets. Since the body is small, a major collision can influence a huge fraction of it all at once. This means one impact does not just create one crater. It can alter slopes, fracture the interior, shift loose material, and help determine the future form of the entire asteroid. A crater on the small asteroid can represent an enormous fraction of that asteroid's total size. This gives asteroid impacts a very different meaning from crater formation on a planet. On Earth, a crater is usually only a local feature relative to the whole planet. On a small asteroid, one crater can dominate the landscape and tell the story of an event that nearly overwhelmed the body itself. Some asteroids survive impacts that might have completely resurfaced or destroyed weaker bodies of similar size. This shows that asteroid strength and structure vary more than simple outward appearance might suggest. Two asteroids of similar size can respond very differently to the same kind of event. One may break apart, while another remains intact and keeps the evidence of its survival. Close planetary encounters can also alter an asteroid's spin state and move loose material on its surface. A near pass by a planet is not just an orbital event. Tidal forces can gently disturb the asteroid's balance, shifting slopes, shaking loose material, and changing how the body rotates. This makes close encounters important chapters in asteroid evolution, even when no collision occurs. The 2029 flyby of Apophis is especially valuable scientifically because it offers a chance to watch how a close planetary encounter can physically affect an asteroid without posing an impact threat to Earth. Scientists will be able to observe whether its surface changes, whether material shifts, and whether its rotation is altered. It is a rare opportunity to study asteroid evolution in real time. Asteroids preserve crater records that document conditions over billions of years. Because they lack weather and active geology like Earth, many of their scars remain visible for immense spans of time. These preserved marks let scientists read long histories of bombardment, disruption, and survival. In a quiet and durable way, asteroid surfaces hold a memory that rocky planets often lose. Near Shoemaker became the first spacecraft ever to orbit an asteroid when it entered orbit around Eros in 2000. That moment changed asteroid science in a very practical way, because for the first time, a mission was not just passing by one of these small worlds, but staying with it and studying it carefully over time. Orbiting an asteroid allowed scientists to map its surface, measure its shape, and understand its gravity much more deeply than a brief flyby ever could. It marked the point where asteroids became places that spacecraft could truly investigate in detail, not just distant targets glimpsed for a moment. Near Shoemaker later made a controlled descent to Eros, which effectively made it the first spacecraft to land on an asteroid. That was an extraordinary technical achievement, because landing on such a small body is nothing like landing on a planet. Eros has weak gravity, an irregular shape, and a surface shaped by countless impacts, so even a gentle descent required careful control. The mission showed that a spacecraft could do more than orbit an asteroid. It could also physically reach the surface and continue gathering information there. Eros has a density that is more similar to rocky material in Earth's crust than to solid iron metal. That helps scientists understand what kind of body it is, because density offers clues about composition and internal structure. If Eros were mostly metallic, it would be much denser. Instead, its measured properties suggest a more stony nature, with material closer to rock than pure metal. This is a good example of how scientists use physical measurements, not just appearance, to work out what an asteroid is really made of. Eros is elongated and heavily cratered, and that tells a long story of repeated impacts over time. Its stretched shape already makes it look different from a round world, but the many craters on its surface show that it has spent an immense amount of time enduring collisions. Each crater is a record of something that struck it in the past. Taken together, they show that even a relatively small asteroid can preserve a very long and busy history, written directly into its surface. Galileo made the first spacecraft flyby of an asteroid when it passed Gaspra in 1991. Before that, asteroids were still mostly known through telescope observations from a distance. The flyby of Gaspra changed that by giving humanity its first close-up look at one of these small bodies. For the first time, people could see an asteroid as an actual landscape with real texture, edges, and scars, rather than just as a point of light moving through the sky. Galileo later flew by Ida in 1993 and discovered Dactyl there. This was a major surprise because it revealed that a small asteroid could have its own moon. That discovery expanded the known complexity of asteroid systems overnight. Instead of thinking of asteroids only as single, isolated rocks, scientists now had clear proof that at least some of them come with companions, which opened new possibilities for understanding how such systems form and evolve. Gaspra and Ida helped prove early on that asteroids are geologically varied worlds rather than simple dots in space. Once the close-up images arrived, it became clear that these objects have structure, surface features, and individual character. They are not all the same, and they are not just leftover rubble in a vague sense. Each one can reflect a different combination of composition, impacts, shape, and history. These early flybys were the beginning of seeing asteroid diversity with our own instruments. At Vesta, the Dawn mission found evidence consistent with a differentiated body that has a crust, mantle, and iron core. That is a very important finding because it means Vesta once behaved more like a developing planet than a simple rock. Internal heating appears to have been strong enough for heavy material to move inward and lighter material to settle above it. This kind of internal organization turns Vesta into a key object for understanding the early stages of planet formation. Dawn also confirmed that Vesta is the source body for the Howardite, Eucrit, and Diagenite meteorites. This was a major success because it linked a specific asteroid to specific meteorites found on Earth. That connection gives scientists a powerful bridge between laboratory study and space exploration. It means that rocks examined in detail on Earth can be confidently tied back to one known asteroid, allowing researchers to compare direct samples with spacecraft observations from the source. Vesta's South Pole hosts enormous impact basins that reshaped much of the asteroid. These basins are so large relative to Vesta's size that they are not just local features. They are global-scale events recorded on a small world. The impacts that formed them changed the asteroid's surface dramatically and likely influenced its interior as well. Looking at those basins is like looking at the memory of a collision, powerful enough to alter a world's future. Those giant impacts on Vesta blasted vast amounts of material into space and helped create the Vesta family of smaller asteroids. In other words, one asteroid's violent history produced a whole related population of fragments. This is one of the clearest examples of how asteroid families can form from catastrophic events. It shows that the belt is not just a collection of unrelated bodies, but also a place where some groups are the descendants of a single shattered past. Vesta is sometimes described as a surviving protoplanet because it formed early and preserved layered internal structure. That description is meaningful because it suggests Vesta is not just an ordinary leftover fragment. It is more like a stalled world, one that began developing along a planet-like path, but never grew large enough to become a full planet. By studying Vesta, scientists get to examine a preserved stage of planetary construction. Ceres, unlike Vesta, is rich in water-related minerals and occupies a transition zone between rocky and icy worlds. This contrast is scientifically valuable because it shows that large objects in the asteroid belt did not all evolve in the same way. Some retained signs of water interaction and chemistry that suggest a very different internal and thermal history. Ceres helps scientists explore the boundary between dry, rocky bodies and more volatile-rich worlds. NASA's Psyche mission is traveling to the metal-rich asteroid Psyche. The mission is important because it is aimed at a target unlike the stony and carbon-rich asteroids that often receive attention. By visiting Psyche directly, scientists hope to learn whether it is truly dominated by metallic material and what that tells us about its origin. The mission brings the question of metal-rich asteroids from theory into close-up exploration. Psyche may be the exposed core of an early protoplanet, though that idea is still being tested. If it is true, Psyche would represent something extraordinary: inner planetary material normally hidden deep inside a larger body, now exposed because of ancient collisions. Even if the final answer turns out to be more complicated, the possibility itself makes Psyche one of the most intriguing asteroids known. It may hold clues to a part of planet building we almost never get to see directly. Studying Psyche could reveal what metallic interiors of planet-building bodies are like without drilling into a planet. That is what makes it so scientifically attractive. On Earth or Mars, the deep metallic interior is hidden far below the crust and impossible to access directly. But if Psyche preserves material related to such an interior, then one small asteroid may provide a rare natural shortcut into a normally unreachable part of planetary structure. Psyche's shape is irregular and potato-like rather than spherical. This detail matters because even potentially metal-rich asteroids are not guaranteed to be smooth or neatly shaped. Its form reminds scientists that small body gravity is usually too weak to force perfect roundness. So even an object that may hold clues to a planetary core still looks like an asteroid in its external shape, with all the irregularity that term suggests. Cleopatra is a dog-bone-shaped asteroid with two small moons named Helios and Cleoslene. Its appearance is one of the strangest among known asteroids, and its moons make the system even more interesting. Because the moons orbit the main body, scientists can use their motion to estimate Cleopatra's mass and infer more about its density and internal structure. So its oddity is not just visually striking. It also makes the system especially useful scientifically. Cleopatra's unusual shape likely reflects a violent collisional history followed by reaccumulation. This means that the asteroid may not have always looked the way it does now. It may have been reshaped by impacts, broken, and then gravitationally reassembled into its current form. That interpretation fits a broader pattern in asteroid science, where many bodies turn out not to be pristine originals, but the products of repeated damage and survival. Donald Johanson is a main belt asteroid that Lucy flew past in 2025 on the way to the Trojan swarms. Although it is not one of Lucy's final Trojan targets, it still serves an important role. Flybys like this allow mission teams to test instruments, gather useful science, and practice navigating around small bodies. Even a stop along the way can become a meaningful opportunity to study asteroid shape, surface features, and history. Donald Johanson appears to be a fragment from a collision that happened about 150 million years ago. That gives it a fairly specific place in collisional history compared with much older solar system material. It reminds scientists that not all asteroid stories go back unchanged to the earliest formation era. Some bodies are much younger in their present form, having been created when larger parents broke apart relatively recently on geological timescales. Lucy is the first mission dedicated to exploring Jupiter's Trojan asteroids. This matters because the Trojans may preserve especially ancient material in stable orbital regions, and until Lucy, they had never been examined up close by a dedicated mission. By going to several targets instead of just one, Lucy gives scientists the chance to compare multiple Trojan worlds and see whether they form a uniform class or a much more varied population. Jupiter Trojans share Jupiter's orbit around the Sun, but gather around stable regions ahead of and behind the planet. These special regions are gravitationally balanced in a way that allows asteroids to remain there for immense spans of time. That makes the Trojans a particularly valuable population for studying long-term solar system history. Their stability has helped them preserve information that may otherwise have been lost. The two Trojan groups are often called the Greek camp and the Trojan camp. This naming tradition is based on characters from the Trojan War and gives the two populations a memorable identity. While the names themselves are cultural, the scientific point is that the asteroids occupy two different gravitationally stable swarms associated with Jupiter's orbit. The naming system helps organize a population that is both large and historically important. Trojan asteroids are thought to preserve primitive material from early solar system history. Because they have remained in stable regions for so long, they may preserve clues about where they formed and how material moved around in the young solar system. Studying them can therefore help answer larger questions about planetary migration and early chemical distribution, not just the history of one asteroid group. Because Trojan asteroids occupy stable gravitational zones, they can survive there for immense stretches of time. That stability is important because it means they have not been constantly scattered or erased. Instead, many of them have remained in place long enough to act as long-term records of early solar system populations. In a sense, their orbital stability has helped preserve their scientific value. Lucy's trajectory includes flybys of one main belt asteroid and several Trojan targets, including binary systems. This design is especially useful because different targets can reveal different kinds of information. A single object may teach scientists about surface geology, while a binary system can also reveal mass and density through mutual orbital motion. By visiting many targets, Lucy increases the chances of finding patterns as well as surprises. Binary Trojans are especially useful because their mutual orbits help scientists measure masses and densities. These are two of the most valuable physical properties in asteroid science because together with size, they allow researchers to infer composition and internal structure. A binary system therefore offers more than visual interest. It provides one of the best natural tools for figuring out what an asteroid is actually like inside. The Trojan swarms may collectively contain as many objects as the main belt. That possibility shows how significant these populations may be on a large scale. Even though they are less famous than the main asteroid belt, they may represent an enormous reservoir of small bodies. If so, they are not just a side feature of the solar system, but one of its major small body populations. Some asteroids are co-orbital with planets other than Jupiter, including objects that can temporarily share Earth-like orbital patterns. This shows that asteroid dynamics can be subtle and flexible. An asteroid does not need to belong permanently to one simple category. Under the right gravitational conditions, it can move in patterns that echo the orbit of a planet for a time, creating temporary partnerships in motion. Asteroid names become official through the International Astronomical Union's Working Group for Small Body Nomenclature. This is more than a naming ceremony. It provides an organized system so that discoveries are handled consistently and confusion is reduced. With so many objects being found, naming and numbering need to follow clear rules. The process ensures that the growing asteroid catalog remains useful and orderly. An asteroid usually receives a permanent number only after its orbit is well determined. That rule exists because many newly discovered objects are first seen only briefly, and without enough observations, their future positions cannot be predicted with confidence. A permanent number is therefore a sign that the asteroid's identity is secure and that astronomers can reliably track it in the future. Discoverers may propose names, but final approval follows official rules. This system balances creativity with consistency. It allows the people who found the object to suggest something meaningful, but it also ensures that the name fits broader conventions and avoids confusion. In a sky filled with many thousands of small bodies, that structure matters a great deal. Not every asteroid receives a name quickly, and many remain known mainly by number and designation. This reminds us how large the asteroid population really is. Discovery has advanced faster than naming, especially in the age of automated surveys. So while some asteroids become famous, many others remain mostly catalogue entries, still scientifically important, even without memorable names. Provisional designations encode the year and half-month of discovery, along with the object sequence within that interval. This system may look technical at first, but it is extremely practical. It gives scientists a fast way to identify when an object was first observed and how it fits into the stream of discoveries from that period. Before an asteroid gets a number or a name, the designation serves as its structured identity. The Minor Planet Center acts as a key clearinghouse for asteroid observations and orbital data. This role is essential because observations come from many telescopes and observers around the world. The center helps gather, organize, and distribute this information so that discoveries can be confirmed, orbits refined, and future observations coordinated. It is one of the quiet institutions that keeps asteroid science working smoothly. Modern asteroid discovery relies heavily on automated sky surveys. Instead of waiting for astronomers to notice moving points of light by eye, large telescopes now scan wide areas of sky repeatedly and use software to detect motion. This has transformed asteroid science by dramatically increasing the number of discoveries and making detection faster, more systematic, and more complete than in earlier eras. Wide-field survey telescopes repeatedly scan the sky to spot moving points of light against the background stars. The repeated scanning is important because motion is what reveals the object as an asteroid rather than a fixed star. By comparing images taken at different times, computers can identify which points have shifted. This is the basic method through which many modern asteroid discoveries are made. Computers can link short observation arcs into candidate orbits, but human checking still matters for quality control. Automated systems are powerful, but they are not perfect. False detections, image artifacts, and confusing cases still need careful review. This balance between machine efficiency and human judgment is part of what makes asteroid discovery both modern and reliable. Follow-up observations are crucial because an asteroid can be lost if its orbit is not refined quickly. A first detection only gives a rough starting point. Without more observations, the uncertainty grows, and the object may become impossible to relocate later. So discovery is only the beginning. The real work includes making sure the asteroid remains trackable over time. An asteroid discovered on one night may be impossible to recover later if too little data were obtained. This is one reason astronomers move quickly after a new detection. The sky is vast, and a small object can easily disappear into uncertainty if its path is not pinned down. Recovery work is therefore an essential part of asteroid science, not just an optional extra. Near-Earth object surveys prioritize finding asteroids large enough to pose significant regional or global hazards. This focus reflects practical concerns in planetary defense. While countless small objects exist, the larger ones deserve special attention because they could do far more damage in the unlikely event of an impact. Search strategies are therefore shaped not only by science, but also by risk management. Size estimates for asteroids are often uncertain until reflectivity is measured. because a dark, large asteroid and a bright, smaller asteroid can appear equally bright. This is a very important detection issue. Brightness alone does not tell you size. To know whether an object is large and dark or smaller and reflective, scientists need more information. Without that, visual appearance can be misleading. Infrared observations help solve that problem by constraining how much heat an asteroid emits. Because warmer objects radiate energy in infrared wavelengths, this kind of measurement gives scientists another way to estimate size. Combined with visible light observations, infrared data helps separate reflectivity from actual physical dimensions. In simple terms, they help turn a bright dot into a better understood object. NASA, WISE and NEO-WISE observations improved size and albedo estimates for many asteroids. These missions were especially useful because they observed in infrared, which is exactly the kind of data needed to refine those properties. By improving both size and reflectivity measurements, they made asteroid catalogues more physically informative, not just positionally accurate. Asteroids are harder to study directly on the inside than on the outside, so scientists infer their interior properties from clues such as density, spin, gravity, radar, and the effects of impacts. This detective work is one of the most interesting parts of asteroid science. Since no one can simply cut one open and look inside, researchers must build a picture from indirect evidence. The result is careful inference rather than direct viewing. A low bulk density can indicate ice, high porosity, or a rubble pile structure rather than a solid monolithic rock. Density is therefore one of the most useful clues in asteroid science. If an object is too light for its size, something important must explain that difference. It may contain empty spaces, loose packing, or volatile-rich material. So density becomes a window into hidden internal structure. Measuring the orbit of an asteroid's moon is one of the best ways to determine the mass of the primary body. This works because orbital motion is governed by gravity. If scientists know how fast the moon moves and how far away it is, they can calculate how much mass must be present in the asteroid it orbits. That makes moons incredibly valuable tools for understanding asteroids in a quantitative way. Once both mass and size are known, scientists can calculate density and make better guesses about composition and internal structure. This is why binary systems and careful shape measurements are so useful together. Size alone is not enough, and mass alone is not enough. But once both are available, researchers can begin to tell whether an asteroid is dense, porous, metallic, rocky, or loosely assembled. Some asteroids have densities so low that they must contain large empty spaces if they are made mostly of rocky material. This is one of the clearest signs that not all asteroids are compact solids. A body can look substantial from the outside, while still being loosely packed within. These low-density cases strongly support the idea that many asteroids are rubble piles with significant internal voids. Other asteroids are dense enough to suggest they contain a substantial amount of metal. In these cases, the physical measurements point in the opposite direction, toward a more compact and heavy internal makeup. Comparing low-density and high-density asteroids helps reveal the astonishing diversity of the asteroid population. Some are airy and loosely assembled, while others seem far more solid and metal-rich. Not every grouping of asteroids that looks similar in orbital space turns out to be a true family. At first glance, some objects may seem related because they travel along somewhat similar paths around the Sun. But when scientists study their compositions more carefully, the picture can change. Two asteroids can move in ways that look connected while actually coming from different parent bodies. This is why composition matters so much. Orbital similarity is a useful clue, but it is not always enough on its own to prove a shared origin. An asteroid collision can have very different outcomes depending on the size, speed, angle, and strength of the bodies involved. Some collisions are catastrophic enough to completely disrupt a parent body, breaking it apart into many fragments. Others are less extreme and may leave the main body mostly intact while still creating a crater family. This range of outcomes is important because it shows that asteroid history is not shaped by one simple kind of impact. Instead, the belt records everything from deep scars to total destruction. Many small asteroids may not be untouched leftovers from the earliest solar system at all. Instead, they may be reaccumulated fragments from larger bodies that were shattered long ago. In simple terms, a small asteroid that looks like one object today may actually be made from pieces of something older. This changes how scientists think about asteroid identity. Some bodies are ancient survivors, but many others may be rebuilt descendants of earlier worlds that no longer exist in their original form. A rubble pile asteroid is made of many pieces held together mostly by gravity rather than by the strength of one solid rock. That means it behaves differently from a monolithic asteroid. If it is disturbed by an impact, spin-up, or spacecraft interaction, its response can depend on how all those internal pieces are packed together. A rubble pile may look like one object from the outside, but inside it may be more like a loose assembly of stones and boulders resting in a weak gravitational balance. Rubble pile asteroids can contain internal voids and uneven density patterns. This means their interiors may be far from smooth or uniform. Some regions can be packed tightly with large blocks, while others may contain more open space or smaller fragments. This matters because the hidden arrangement inside the asteroid helps determine how it responds to stress, impacts, and rotation. Two asteroids of similar size can behave very differently if one is tightly packed and the other is full of gaps. Bennu appears to have a less dense interior region, which shows that even a small asteroid can be internally heterogeneous. In other words, it is not necessarily made of the same kind of material, packed in the same way, from the outside all the way in. This finding is important because it tells scientists that asteroid interiors can be more complicated than simple models suggest. A body may look unified in images, yet still contain important internal differences. Because gravity is so weak on a small asteroid, even a pebble tossed upward could travel a very long distance before falling back, if it comes back at all. That helps put the environment into perspective. On Earth, gravity dominates every movement of loose material, but on a tiny asteroid, the rules are gentler and stranger. A small nudge can produce a surprisingly large result. This week, gravity shapes how particles move, how landers behave, and how impacts redistribute debris. Escape velocities on small asteroids can be only a few tens of centimeters or a few meters per second. That is extremely low by everyday standards. It means that material does not need much speed to leave the asteroid entirely. A mild impact or a modest disturbance can throw dust, pebbles, or fragments away into space. This is one reason asteroid surfaces can change so easily, and why debris can be lost rather than simply settling back nearby. That weak gravity makes spacecraft navigation around asteroids much more delicate than navigation around planets. Around a large planet, gravity provides a stronger and more predictable environment for orbiting spacecraft. Around a tiny asteroid, everything is more subtle. Small forces matter more, irregular shape matters more, and even the pressure of sunlight can begin to affect motion. Missions to asteroids therefore require extremely careful design and constant awareness of tiny influences. Instead of flying down onto an asteroid the way an aircraft might approach a runway, asteroid landers often need to hop, bounce, or anchor very carefully. The reason is simple. Touchdown speeds must be extremely low. If a spacecraft arrives too fast, even by a little, it may rebound or destabilize itself in the asteroid's weak gravity. This makes landing on an asteroid a very different challenge from landing on a planet with thick gravity and a more predictable surface response. Mascot, a small lander carried by Hayabusa 2, bounced on Ryugu and studied the surface in place. This was a useful demonstration of how operations on a tiny asteroid must adapt to weak gravity rather than fight it. Instead of relying on ordinary mobility methods, Mascot used the environment as it was. Once on the surface, it helped scientists gather direct information about the asteroid's texture, composition, and local conditions, showing how much can be learned even from a small instrument package. Minerva rovers deployed at Ryugu moved by hopping because wheels are not very effective in such low gravity. On Earth or Mars, wheels work because they press firmly against the ground. On a tiny asteroid, that pressure is so weak that wheels can fail to grip in a useful way. Hopping becomes a more practical solution. This is a wonderful example of how asteroid exploration often requires rethinking ordinary engineering ideas from the ground up. Philae was a comet lander rather than an asteroid lander, but the lessons from it influenced thinking about anchoring on small bodies. Missions like that teach engineers how difficult it can be to attach to or remain stable on a weak gravity object. Even though a comet and an asteroid are not the same, both belong to the broader class of small bodies, where normal landing assumptions can fail. Experience from one kind of mission can therefore improve design strategies for another. Artificial impacts are useful in asteroid science because they let researchers study subsurface material that has not been altered as much by sunlight and space weathering. The topmost layer of an asteroid is often the most changed part because it has spent the longest time exposed to radiation, micrometeorites, and temperature cycling. By deliberately creating a crater, scientists can expose fresher material from below and compare it with the weathered surface above it. The crater made on Ryugu exposed deeper material, but could then be sampled. This was scientifically valuable because it gave researchers a controlled way to study what lies beneath the altered outer layer. Material from below the surface may preserve older chemical and physical characteristics closer to the asteroid's original state. So the artificial crater was not just a dramatic event. It was a carefully planned method for accessing a deeper record of asteroid history. Subsurface samples are especially useful because they allow scientists to compare fresh and weathered asteroid material directly. That comparison can reveal how much change is caused by long exposure to space. It helps researchers separate original properties from later surface modifications. In a simple way, it is like comparing the outside of an old object with a newly opened interior. The difference tells you what time and environment have done. Asteroids can contain metal, silicate rock, carbon compounds, sulfides, hydrated minerals, and other combinations of material. This broad diversity means that asteroid science is really a study of many different kinds of worlds, not one simple category. Some asteroids preserve dry rocky histories, some record metal-rich origins, and some show signs of water-related chemistry. The range of materials tells us that the solar system sorted and transformed matter in many different ways very early on. Some metal-rich asteroids may preserve material linked to the cores of disrupted protoplanets. If that is true for specific cases, then studying them could give scientists access to the kind of material that normally sits hidden deep inside larger worlds. On planets, that interior is buried far below the surface and cannot be reached directly. But a broken early body may have exposed its inner regions through collision, turning an asteroid into a rare sample of planetary interior material. Other asteroids never became hot enough to melt, and instead remained chemically primitive. That means they avoided the kind of internal restructuring that separates metal and rock into layers. These bodies are valuable because they preserve more original solar system material. Rather than showing how a world evolved internally, they show what the starting ingredients looked like before strong heating changed them. They're like preserved early chapters rather than transformed later ones. Short-lived radioactive isotopes in the early solar system helped heat some parent bodies from the inside. These unstable atoms released energy as they decayed, and in the first few million years of solar system history, that energy could be strong enough to warm small worlds significantly. Whether an asteroid formed early enough to trap that heat could determine whether it remained primitive or underwent major internal change. Timing, in this case, made a tremendous difference. If an early asteroid became hot enough, heavy metal could sink inward, while lighter rocky material rose outward, creating internal layering. This process is called differentiation, and it is one of the most important steps toward a planet-like structure. It turns a mixed body into one with a more ordered interior. Some asteroids appear to preserve evidence that this happened, which means they once moved partway along the same developmental path, followed by larger rocky planets. Vesta is one of the clearest examples showing that differentiation happened in at least some asteroid-sized bodies. That makes it an especially important object in planetary science. It proves that even a body much smaller than a planet can still experience major internal evolution if conditions are right. Vesta, therefore, acts as a bridge between simple primitive asteroids and more fully developed terrestrial worlds. Spacecraft images show that asteroid craters come in many forms, from sharp, bowl-shaped pits to older, more subdued basins. This variety helps scientists interpret age and surface history. Fresh craters usually have clearer edges and more distinct structure, while older ones may be softened by later impacts, surface motion, or slow degradation processes. By comparing crater shapes, researchers can begin to read the relative timeline of what happened on an asteroid's surface. On low-gravity bodies, crater ejecta can travel far and may even escape into space entirely. This changes the whole character of impact processes. On a large planet, much of the blasted material falls back nearby. On a small asteroid, the same event may throw debris far away or lose it altogether. That affects how craters look, how surfaces are resurfaced, and how fragments from one body can eventually become independent objects. Some asteroids preserve giant grooves or ridges linked to impacts or internal structure. These long features show that stress on a small body can be expressed over large parts of the surface. A major impact does not only dig a crater, it can also send shock through the asteroid, fracture the crust, or reveal something about the way the body is built inside. Grooves and ridges therefore act like large-scale clues to both impacts and internal mechanics. Eros has a long surface ridge that help reveal its elongated structure. A ridge like that is more than just a surface decoration. It reflects the overall form and mechanical history of the asteroid. By studying such features, scientists can better understand how the body responded to impacts, internal stress, and its own shape. Surface landforms on asteroids often tell a larger story about the whole object. Ida's heavily cratered surface suggested a long and violent collisional past. The density and variety of craters show that the asteroid spent a very long time being struck by smaller objects. Each impact added another mark, and together those marks built up a visible history of repeated bombardment. Ida helps show that even relatively small asteroids can preserve a record of many separate events across immense spans of time. Asteroids can undergo global reshaping after large impacts because shock waves move through their small bodies differently than they do through larger planets. Since the whole object is small, a single major impact can influence a large fraction of it. Slopes may shift, loose material may move, and fractures may spread widely. On an asteroid, one strong event can become a body-wide process rather than just a local disturbance. A crater on a small asteroid can represent a huge fraction of the object's total size. That makes asteroid impacts especially dramatic in proportion to the body itself. On Earth, even a large crater is still small compared with the whole planet. On a tiny asteroid, one crater may dominate the landscape and define much of the object's appearance. This scaling difference is one reason asteroid geology looks so extreme. Some asteroids survive impacts that would have completely resurfaced or destroyed weaker bodies of similar size. This tells scientists that internal structure matters enormously. Strength, porosity, packing, and composition all influence how an asteroid handles a collision. Two bodies may look similar from the outside, yet one can endure a major event while the other would come apart. That hidden difference is one of the reasons asteroid behavior is so varied. Close planetary encounters can alter asteroid spin states and change surface slopes. Even without a collision, the gravity of a nearby planet can subtly disturb a small body. Loose material may shift, the rotation may change, and the surface may be shaken. This shows that asteroid evolution is shaped not only by impacts and sunlight, but also by gravitational encounters that leave no crater at all. Tidal forces during a very close Earth flyby can shake an asteroid and move loose material downslope. This is important because it provides a mechanism for surface change that does not require impact. If a small asteroid passes close enough, Earth's gravity can pull unevenly on different parts of it, gently disturbing the balance of surface material. Over time, this can modify slopes, expose new areas, or rearrange loose regolith. That is one reason the 2029 passage of Apophis is scientifically valuable even though it poses no impact threat. Scientists will have a chance to observe how a close planetary flyby affects a real asteroid in detail. It is a natural experiment on a grand scale, happening safely enough to study without danger. Researchers hope to learn whether the surface shifts, whether spin changes, and how tidal effects appear on a small body in practice. Asteroids can sometimes be the parents of meteor streams, although comets are more commonly responsible for the major meteor showers seen from Earth. This matters because it shows that asteroid material is not always confined to the asteroid itself. Fragments can spread along an orbit and create visible effects when Earth passes through them. While less common than comet-based streams, asteroid-linked streams still help connect small body science to observations in our own sky. Asteroid fragments that survive passage through Earth's atmosphere become meteorites. This gives scientists a direct physical connection between objects in space and samples on the ground. A meteorite is not just an interesting rock. It can be a piece of an asteroid's crust, interior, or fragmented history. These physical samples are one of the great strengths of asteroid science because they allow laboratory study of real extraterrestrial material. Most incoming meteoroids burn up entirely before they reach the ground. That is why meteorites are special rather than ordinary. Earth's atmosphere acts as a filter, destroying many small pieces before they can land. The ones that survive tend to be larger, stronger, or entering under the right conditions. This means that every recovered meteorite represents both a fragment of space and a successful journey through a destructive atmospheric passage. The Chelyabinsk event in 2013 showed that even a relatively modest asteroid can create a dangerous airburst and widespread shock damage. The object did not need to make a crater to be hazardous. It exploded in the atmosphere, and the shockwave damaged buildings and injured many people, mostly through shattered glass. This event reminded the world that asteroid risk includes atmospheric explosions as well as direct ground impacts. The Tunguska explosion in 1908 is widely interpreted as the atmospheric breakup of an asteroid or cometary body. Although it happened long before modern space monitoring, the event remains one of the most powerful examples of what a small cosmic body can do without leaving a classic impact crater. The explosion flattened a vast forested area, showing that airbursts can release enormous energy, even when the object never reaches the ground intact. Planetary defense, therefore, has to consider both ground impacts and airbursts. An incoming object does not need to strike the surface directly to cause serious damage. Its size, speed, composition, and entry angle all influence whether it breaks apart in the atmosphere or reaches the ground more intact. This is why asteroid hazard planning is broader than simply asking where a crater might form. Small asteroids strike Earth much more often than large ones, but truly catastrophic impacts are far rarer. This pattern is important because it helps scientists think realistically about risk. The most devastating events are the least common, while smaller and less destructive objects are much more frequent. The challenge of planetary defense is to understand the whole spectrum, from common small events to rare but much larger threats. Crater counts on airless bodies help scientists estimate the relative ages of surfaces across the solar system. The general idea is that older surfaces have had more time to collect impacts, so they tend to preserve more craters. This method is not perfect, but it is one of the most useful ways to infer relative timing where no direct samples are available. Asteroids, moons, and other airless bodies can all be studied in this way. Asteroids themselves preserve crater records that document conditions over billions of years. Because they do not have rain, rivers, or tectonic plates to erase their scars the way Earth does, many of those marks remain visible for extraordinary lengths of time. A cratered asteroid surface can therefore function as a long-term record of bombardment history and surface change. Because there is no weather on asteroids, even very ancient scars can survive on their surfaces. On Earth, erosion and geological activity steadily erase the record of old impacts. On an asteroid, the absence of atmosphere and flowing water means surface features can remain far longer. That makes asteroid landscapes particularly valuable for preserving ancient evidence that would vanish on a more active world. Even so, asteroid surfaces are not completely static. Impacts, spin changes, thermal fracturing, and landslides can continue modifying them over time. This is an important balance in asteroid science. Surfaces are preserved better than on Earth, but they are not frozen forever. Change still happens, just through different processes. The result is a surface that can be ancient and active at the same time. Thermal cracking can slowly break boulders apart as day-and-night temperature swings repeatedly stress the rock. On an airless body, temperatures can shift sharply between sunlight and shadow, causing materials to expand and contract again and again. Over long periods, this repeated stress weakens the rock and breaks it down. So, even without water or wind, an asteroid can gradually create new fragments through temperature alone. Asteroid interiors are difficult to study directly, so scientists infer them from density, spin, radar, gravity, and seismic clues from impacts. This indirect method is a central part of asteroid research. Since no one can look inside directly, researchers build a picture from outward behavior and measurements. The process is careful and layered, using many kinds of evidence together to estimate what lies beneath the surface. A low bulk density can point to ice, empty space, or a rubble pile structure instead of a single solid rock. That is why density is such a powerful clue. If an asteroid is lighter than expected for its size, then something inside it must explain the difference. It may not be tightly packed, or it may contain materials less dense than solid stone or metal. Density is therefore one of the best ways to begin understanding internal structure. Once scientists know both mass and size, they can calculate density and make better judgments about composition and internal structure. This combination is far more useful than either measurement alone. A large asteroid can still be surprisingly light, and a small one can be surprisingly dense. Only by combining mass and volume can researchers begin to understand whether a body is porous, metallic, rocky, or loosely assembled. Some asteroids have densities so low that, if they are mostly rocky, they must contain large void spaces inside. This strongly supports the idea that many are not compact solid objects. Instead, they may be made of blocks and fragments with empty gaps between them. These hidden spaces are important because they affect strength, impact response, and the way the asteroid evolves over time. Other asteroids are dense enough to suggest a substantial metal content. These cases help round out the full range of asteroid diversity. Not all asteroids are fragile rubble piles or dark, primitive bodies. Some appear much more compact and heavy, pointing toward compositions richer in metal. By comparing low-density and high-density objects, scientists gain a clearer picture of how many different kinds of small worlds the solar system contains. The distribution of asteroid types across the main belt is not random. Scientists have found that certain kinds of asteroids are more common in some regions than in others, and this pattern tells an important story about the early solar system. If the belt were just a completely mixed collection of bodies, we would not expect such clear trends. Instead, the arrangement suggests that temperature, distance from the Sun, and later gravitational reshuffling all played roles in deciding where different materials ended up. Darker CT-type asteroids are more common in the outer belt, while stonier S-type asteroids are more common in the inner belt. This makes sense when scientists think about how temperature changed with distance from the young Sun. Closer in, hotter conditions favored materials and histories different from those farther out. The result is that even today, the asteroid belt preserves a broad chemical map of the early solar system, with different regions holding different kinds of surviving bodies. That overall pattern reflects temperature differences in the early solar nebula, along with later mixing of material. In the young solar system, not every region had the same conditions. Heat, chemistry, and particle behavior varied with distance from the Sun. But the story did not stop there. The motions of giant planets and countless collisions later stirred that material around. So the asteroid belt is not a perfectly untouched fossil, but it still keeps traces of how the early solar system first sorted itself. Asteroids are clues to the way the young solar system sorted matter by distance from the Sun. Materials that could survive or form in hotter regions differed from those in colder zones. By studying asteroid types and where they are found, scientists can reconstruct part of that original pattern. In this way, asteroids act like small, preserved samples from different neighborhoods of the solar system's youth. At the same time, giant planet migration may have mixed material from different zones, so today's asteroid belt is not a simple, untouched fossil bed. Large planets like Jupiter and Saturn may not have stayed exactly where they formed. If they moved early in solar system history, their gravity could have scattered smaller bodies, pulling some inward and pushing others outward. That means the modern belt may contain a mixture of native residents and bodies that came from elsewhere. Models of solar system evolution often use asteroid populations to test how Jupiter and Saturn may have migrated early on. This is because asteroids are sensitive to gravitational disturbance, and their current distribution can preserve the signature of old planetary movements. If a model of giant planet migration produces the wrong kind of asteroid belt, scientists know it likely missed something important. So asteroids help test large-scale theories about how the entire solar system developed. Some asteroids preserve magnetization or mineral evidence that records ancient thermal events. This is valuable because it means these bodies can hold memory of heating episodes that happened billions of years ago, That memory may be stored in the arrangement of atoms in minerals, or in signs of how rock changed under specific temperatures. In effect, some asteroids and meteorites keep a faint record of ancient internal or environmental conditions. Laboratory work on meteorites let scientists date these ancient events with very high precision. Once a meteorite is linked to asteroid processes, researchers can use powerful techniques to determine when heating, melting, or shock events occurred. This turns a stone found on Earth into a time capsule from deep history. It is one of the remarkable strengths of asteroid science that direct samples can be studied with extraordinary detail. That is why a small rock in a museum can provide timing information about processes that happened before Earth fully formed. A meteorite may seem humble from the outside, but it can contain minerals that locked in a record from the earliest solar system. By reading that record carefully, scientists can reconstruct when certain bodies formed, when they heated up, and when they were broken apart. A small sample can therefore reveal events from an age far older than any rock formed later on Earth's surface. Asteroids are useful to comparative planetology because they bridge the gap between dust grains and planets. They are not as tiny as dust and not as fully developed as large planets, but they occupy the middle ground where many formative processes took place. Studying them helps scientists understand how small particles gradually became larger bodies, and how some of those bodies began to develop complex internal histories. They also show that planet formation was an inefficient and violent process, leaving behind many survivors and fragments. Not all the material in the young solar system ended up in planets. Some of it remained in smaller bodies, and some was repeatedly broken apart and reassembled. The asteroid population is therefore evidence that planet formation was not smooth or complete. It was messy, competitive, and full of interruption. The main belt contains millions of objects larger than 1 kilometer, and vastly more smaller ones. This shows that the asteroid population is enormous, even if most of those bodies are too small to become famous individually. The belt is not dominated only by a few named asteroids. It is a huge collection of bodies across many size ranges, each one participating in the larger dynamical and collisional life of the region. Even so, the total amount of material in the main belt is tiny compared with a planet. This is a very important big-picture fact. Even though there are many objects, their combined mass is still small. That means the belt is not a failed planet in any simple sense. It is better understood as a depleted region containing survivors and fragments, not a place where a full-sized world is waiting in pieces. Some researchers think the original asteroid region once held much more mass that was later depleted. If that is true, then the present belt is only a thin remnant of what used to be there. Gravitational disruption, collisions, and planetary migration may have removed a very large amount of material over time. This helps explain why the belt today contains so many interesting bodies, yet still has such a low total mass. Impacts among asteroids in the main belt are usually slow enough to shatter bodies rather than melt them completely. This matters because it affects what kind of fragments are produced. Instead of turning everything into molten material, these collisions often break objects apart mechanically. That helps preserve mineralogical clues and creates families of fragments that still reflect the parent body's original makeup. Repeated impacts over billions of years grind down large bodies and create families of smaller fragments. This gradual process means the belt is constantly being reshaped, though on timescales far beyond human life. A large body may survive many impacts before eventually being broken apart, and its fragments can then be struck again. Over immense spans of time, the asteroid belt becomes a place of slow but relentless recycling. The smallest asteroids can have very short dynamical lifetimes because collisions or solar heating processes destroy them relatively quickly. In other words, tiny bodies are often temporary on cosmic timescales. They are more vulnerable to being broken apart, altered, or driven into new orbits. This means the smallest members of the asteroid population may need to be replenished continuously by the breakup of larger bodies. Objects that pass extremely close to the Sun may crack, shed material, or be thermally altered beyond what minebelt asteroids experience. The Sun is not just a source of light. At very close range, it becomes an intense physical force that can stress and transform a small body. Asteroids that venture inward can therefore experience histories very different from those that remain farther out in the main belt. Some near-Earth asteroids are extinct or dormant comet-like bodies, so the boundary between categories is not always absolute. This is an important reminder that solar system categories are useful, but nature does not always obey them neatly. Some objects may look asteroid-like now, even if they once behaved more like comets. The difference between rocky and icy histories can blur in certain cases, especially after long exposure to sunlight. Asteroids and comets overlap within a broader population of small solar system bodies. While the two groups are often described separately, they belong to a larger family of leftover objects from solar system formation. Some are rocky, some are icy, and some sit in between in ways that challenge simple labeling. This overlap makes the study of small bodies richer and more complex than a strict divide would suggest. Still, asteroids are generally defined as being made mostly of rock or metal, and as lacking the active tails typical of comets. This working definition is useful because it gives scientists a practical way to separate the most familiar members of the two groups. Even if some borderline cases exist, most asteroids fit this description well. They are solid, airless, and inactive compared with the brighter, more visibly active comets. When an asteroid is first found, astronomers must determine whether its orbit is secure enough to avoid confusion with other objects. That early stage is very important because many newly discovered points of light could be lost or misidentified if their motions are not tracked carefully. Establishing a secure orbit means turning a brief sighting into a real, reliable object in the scientific record. Recovered pre-discovery images, called precoveries, can greatly improve an asteroid's orbit by extending the observed arc backward in time. If astronomers find that the asteroid had actually been recorded in older images before it was officially discovered, those earlier positions become extremely valuable. They add more data over a longer time span, and that sharply improves orbital accuracy. It is like suddenly discovering that a history once thought short is actually much longer. Sky surveys sometimes rediscover asteroids that had been lost for decades. This happens when an object was seen too briefly in the past for its orbit to be fixed securely. Later, improved technology and repeated scanning may find it again. Recovering a lost asteroid is scientifically satisfying because it restores a missing body to the catalogue and reconnects older observations with modern data. Space missions to asteroids often use ion propulsion because it is efficient for long, flexible journeys among small bodies. Ion engines provide gentle thrust over long periods rather than short, powerful bursts. That makes them well suited for missions that need to change speed gradually and match the orbit of a moving asteroid. In deep space exploration, efficiency can matter more than raw force. Dawn and Hayabusa 2 both demonstrated the value of ion engines in asteroid exploration. These missions showed that low-thrust propulsion can successfully support detailed scientific travel in the solar system. Instead of treating ion propulsion as experimental, they proved it could be practical and reliable for reaching difficult targets and carrying out complex plans around small worlds. Low-thrust propulsion is especially useful when a mission must match the orbit of a small moving target rather than simply rush past it. A flyby requires timing and speed, but rendezvous demands much more control. The spacecraft must gradually shape its path until it moves along with the asteroid. Ion propulsion is well suited to this kind of careful, patient orbital work. Sampling an asteroid is mechanically difficult because surface properties can be very different from what scientists expected. From far away, a surface may seem straightforward, but once a spacecraft arrives, the material may turn out to be looser, rougher, or more unpredictable than models suggested. This is one reason asteroid missions often deliver surprises, even after years of planning. OSIRIS-REx found Bennu's surface to be much less cohesive than expected, which allowed the sampler to sink in dramatically. This was a striking result because it showed that the asteroid's surface did not resist the spacecraft the way a firmer surface would. Instead, the material behaved as if it were very loosely bound. That discovery changed scientists' understanding of Bennu's near-surface structure in an immediate and physical way. That result showed that even detailed close-up asteroid models can miss key realities until a spacecraft physically interacts with the surface. Images, spectra, and remote measurements are powerful, but they do not tell everything. Direct contact can reveal how tightly material is packed, how it moves, and how it responds to force. Bennu reminded scientists that touching an asteroid can teach lessons that observation alone cannot provide. Asteroid mission designers must plan for uncertainty in gravity, boulder fields, dust behavior, and communication delays. Every one of those factors matters more around a small body than people might first assume. Weak gravity changes motion, rough terrain complicates navigation, dust can behave unexpectedly, and spacecraft far from Earth cannot rely on instant instructions. Designing such missions means planning not just for known conditions, but also for surprise. Because many asteroids are tiny, a spacecraft can orbit them only in a loose and carefully managed way. Around a planet, an orbit can feel stable and familiar. Around a small asteroid, the same idea becomes more delicate because the gravitational pull is weak and the shape is irregular. The spacecraft often has to follow paths that are much more actively controlled and cautiously designed. In some cases, spacecraft do not truly orbit an asteroid in the usual sense, but instead follow carefully controlled trajectories shaped by both gravity and solar pressure. This reflects how different the environment is around a small body. The spacecraft is not simply falling around a massive sphere. It is moving in a setting where several weak forces all matter at once, and the path must be maintained with great care. Sunlight itself matters more around asteroids because their gravity is so weak that radiation pressure can affect spacecraft motion. Around a large planet, this effect is usually minor compared with gravity. Around a tiny asteroid, even the gentle push from sunlight can become important. This is one of the subtle but beautiful aspects of small body exploration. Light itself becomes part of the navigation problem. The first close-up asteroid images transformed asteroids from abstract catalog entries into real landscapes. Before those missions, asteroids were mostly numbers, designations, and distant points of light. Close-up images changed that instantly. They revealed cliffs, craters, boulders, ridges, and odd shapes. A category of objects once known mostly through mathematics became visible as a collection of actual places. Caspera showed a battered, angular surface that looked nothing like a miniature planet. It did not resemble a smooth little world. Instead, it appeared irregular, scarred, and distinctly asteroid-like. That first close-up impression helped set expectations for what many small bodies are really like. Not neat spheres, but rough survivors shaped by impacts and long exposure in space. IDA revealed that small bodies could have moons and unexpectedly intricate topography. This discovery expanded asteroid science in two ways at once. It showed that even a small asteroid can have a satellite system, and it also showed that asteroid surfaces can be more detailed and varied than many expected. IDA became a reminder that close study often reveals more structure than simplicity. Eros demonstrated that a near-Earth asteroid could host ponds of fine material despite weak gravity. That was surprising because many people assumed loose fine particles would not settle so neatly on such a small body. Yet the asteroid showed smoother deposits in some low areas, suggesting that even in weak gravity, fine material can migrate and collect under the right conditions. Itokawa showed that a tiny body could consist of a jumbled mixture of boulders and smoother terrain. This contrast made it one of the clearest examples of how asteroid surfaces can vary dramatically across short distances. One area may look blocky and rough, while another may show finer material gathered in lower regions. It gave scientists a vivid picture of how weak gravity, impacts, and internal structure interact. Ryugu and Bennu revealed that top-shaped rubble piles are common enough to form a major category of small asteroid structure. Before these missions, that shape was not so central to the picture of asteroid diversity. After them, it became clear that spinning top forms, equatorial bulges, and loose rubble pile organization are not odd exceptions. They are an important part of how many small asteroids exist and evolve. Vesta showed that some asteroids are geologically evolved enough to resemble scaled-down terrestrial worlds. It is still an asteroid, but it carries evidence of processes more often associated with planets, such as internal layering and large-scale geological history. That makes it one of the best examples of how the word asteroid covers a much broader range of worlds than many people first imagine. Ceres showed that the line between asteroid and icy dwarf planet can be scientifically more interesting than the label itself. Rather than worrying only about what category name it receives, scientists focus on what it reveals: water-related minerals, internal complexity, and a position between rocky and icy worlds. Ceres matters because it expands the story of what a body in the asteroid region can be. Psyche may reveal whether metal-rich asteroids are stripped cores, collision products, or something in between. This uncertainty is exactly what makes it such an important target. A close-up mission can help determine whether simple ideas about its origin hold true, or whether the real story is more complex. Either outcome is valuable because it improves our understanding of how metal-rich small bodies form. Trojan asteroids may tell scientists where some primitive bodies originally formed in the young solar system. If their compositions and structures preserve clues to their birthplaces, then studying them can help reconstruct early solar system geography. They may reveal whether material now near Jupiter once formed much farther in or farther out, giving scientists a better map of ancient solar system movement. Every asteroid mission has brought surprises, which is one reason asteroid science keeps expanding so rapidly. The closer scientists get, the more complexity they find. Shapes turn out stranger, surfaces rougher, interiors less uniform, and histories richer than expected. This pattern of surprise is not a weakness of science. It is a sign that these small worlds are far more interesting than their distant appearance first suggests. Asteroid observations also matter for understanding impact history on Earth and other planets. By studying the bodies that cause impacts, scientists can better estimate how often different sizes of collisions occur and what kinds of surfaces they affect. Asteroids are therefore not just distant objects of curiosity. They are also part of the broader story of planetary change, including Earth's own history. Large impacts influenced Earth's biological history and likely affected the habitability of planets repeatedly across time. A major impact can change climate, reshape ecosystems, and alter the course of evolution. This means asteroid science reaches beyond astronomy into geology and biology. To understand Earth's past fully, scientists also need to understand the populations of small bodies that sometimes collide with planets. The Chicxulub impact crater, buried around the Yucatan region, marks one of the best-known asteroid impact events in Earth history. It provides strong geological evidence of a truly enormous collision. Even though the crater is not obvious at the surface in the way a fresh impact might be, the structure remains one of the clearest records of a world-changing asteroid event. Chicxulub is about 180 kilometers across, showing the scale of the impact that helped end the age of Nenathian dinosaurs. A crater of that size tells us that the event was not local or ordinary. It was global in consequence. Studying such impact helps scientists understand not only asteroid hazards, but also how cosmic events can reshape the history of life on a planet. Impact craters on Earth are much harder to preserve than craters on airless bodies such as asteroids, because Earth is always changing its own surface. Rain, rivers, wind, plant growth, glaciers, oceans, and shifting crust all work slowly, but constantly to erase old scars. Over enough time, even a very large impact can become hidden, buried, or reshaped. That is why Earth does not display its ancient impact history as clearly as small, airless bodies do. This is one reason the impact record on Earth is far less complete than the crater record on the Moon or on asteroids. Many ancient collisions almost certainly happened here, but the evidence did not always survive. On worlds without weather and plate tectonics, old craters can remain for immense spans of time. On Earth, the planet keeps rewriting its surface, so the surviving record is only part of the full story. By studying asteroids, scientists can estimate how often impacts of different sizes should happen over long stretches of geological time. This helps researchers compare what the laws of orbital motion predict with the craters that still remain on planets and moons. In that way, asteroid science helps fill in missing chapters of Earth's hidden collision history. Even when our own planet has erased the evidence, the source population still carries part of the answer. Planetary defense has become an international concern because an asteroid threat would not belong to only one country. A large impact, or even a serious regional one, could affect many nations directly or indirectly. That is why asteroid monitoring and response planning are now global efforts. The sky is shared, and so is the responsibility of watching it carefully. The International Asteroid Warning Network exists to coordinate the sharing of information about potentially hazardous asteroids. This matters because timing and clarity are essential when new observations come in. Scientists in different countries and at different observatories need to compare results quickly and accurately. A warning system is most useful when it is organized, cooperative, and based on a common scientific picture. The Space Mission Planning Advisory Group studies how nations might respond if a real asteroid threat were confirmed. That includes thinking about possible space missions, timelines, technical options, and international coordination. In simple terms, it is not enough to detect a dangerous object. There also needs to be a serious plan for what to do next. This group helps turn the idea of planetary defense into something practical and prepared. Discussions of asteroid hazards usually separate the problem into several parts: discovery, orbit determination, physical characterization, and mitigation planning. Each step matters for a different reason. First, the object must be found. Then its path must be measured well. Then its size and structure must be understood. And only after that can a realistic response be designed. This careful sequence shows how asteroid defense depends on knowledge building step by step. An asteroid's size, composition, spin, and structure all matter when scientists think about how to deflect it. Two objects on similar paths might respond very differently to the same attempt at intervention. A dense metallic asteroid, a porous rubble pile, and a rapidly spinning body are not the same engineering problem. So understanding the object itself is just as important as knowing where it is going. A porous rubble pile asteroid may react very differently to a deflection attempt than a solid metallic body would. A loose structure might absorb energy, shift internally, or shed material in complex ways, while a stronger solid object might respond more directly. This is why asteroid mitigation is not simply a matter of applying force. The physical nature of the target shapes the whole outcome. That is one reason missions like DART and HERA are not only about changing asteroid motion, but also about understanding asteroid physics. Deflection is part of the goal, but so is learning how small bodies actually behave when pushed, struck, or observed closely afterward. In a calm and important way, these missions turn a defense concept into a science experiment that improves future preparedness. Not all asteroid research is focused on danger. Asteroids are also important targets for pure science and for possible future resource use. They preserve records of the early solar system, contain a range of valuable materials, and challenge engineers to work in new environments. So while they can represent risk, they also represent knowledge, opportunity, and a deeper understanding of how planetary systems work. Some future-looking ideas focus on mining water from asteroids so it could be used to make rocket propellant in space. Water is useful not only for life support, but also because it can be separated into hydrogen and oxygen, which are important rocket fuels. If water could be obtained without lifting it from Earth, deep space travel might one day become more flexible and efficient. Other proposals imagine extracting metals from suitable asteroids for industrial use beyond Earth. Metal-rich bodies may contain materials that could be valuable if space-based manufacturing becomes practical in the future. These ideas are still mostly in the planning and concept stage, but they show how asteroids are being considered not just as scientific objects, but also as possible working resources in space. Any resource idea depends heavily on the asteroid's composition, orbit, rotation, and mechanical strength. It is not enough for an asteroid to contain useful material in theory. The object also has to be reachable, stable enough to work with, and physically suitable for drilling, collecting, or processing. In this way, asteroid resource planning depends on the same kind of close physical understanding that science missions already seek. Near-Earth asteroids are often favored in mining discussions because bringing material from them could require less energy than transporting it from the main belt. Distance in space is not only about kilometers. It is also about orbital mechanics and how much effort it takes to meet an object and move material afterward. Some near-Earth asteroids may be comparatively accessible, which makes them more attractive for future practical use. Water from asteroids could, in principle, be split into hydrogen and oxygen to supply both fuel and life support systems for deep space missions. That possibility is one reason water-rich asteroids attract interest beyond pure science. A body that preserves ancient hydrated material might also one day help support spacecraft traveling farther from Earth, making the asteroid population relevant to long-term space infrastructure. Even if asteroid mining develops slowly, the technologies built for prospecting, it can still improve asteroid science. Instruments designed to identify composition, map internal structure, or test surface behavior would also be extremely useful for research missions. In that sense, scientific and engineering goals overlap. The effort to understand what an asteroid contains can serve both curiosity and future practical needs. Robotic mining concepts have to solve difficult problems such as anchoring, excavation, dust control, and transport in microgravity. On Earth, heavy machines rely on their own weight and the strong pull of gravity to stay in place while they dig. On a tiny asteroid, that familiar advantage disappears. Every action has to be redesigned for a place where pushing down too hard could push the machine away instead. An excavator that works perfectly on Earth could fail on a small asteroid because pressing into the ground might simply send the machine drifting backward. This simple image explains why asteroid engineering is so unusual. In weak gravity, action and reaction become much more delicate. Tools, anchoring systems, and movement methods must all be redesigned from first principles. Asteroids therefore force engineers to rethink drilling, scooping, and handling loose material in an environment very different from Earth. Even ordinary tasks become strange when gravity is minimal and surfaces may be unstable. Designing for asteroids means understanding both mechanics and the local behavior of regolith, boulders, and dust. These bodies are quiet, but they ask difficult technical questions. Some mission ideas prefer capturing very small asteroids or individual boulders and moving them into safer or more convenient working orbits. This approach avoids the challenge of trying to mine a large body in place. By bringing a smaller target to a controlled location, engineers might simplify access and operations. Even as a concept, it shows how flexible asteroid planning can be. Other ideas favor in situ processing, where raw material is used directly at the asteroid rather than hauled long distances. This could save energy and reduce transport problems if the needed products can be made where the material already is. In that sense, the asteroid becomes both source and workplace. It is a very different vision from bringing everything back to Earth. Asteroids have even inspired habitat concepts, because some thinkers have imagined reshaping or hollowing them into radiation-shielded settlements in space. These ideas remain speculative, but they are scientifically interesting. A solid body in space already provides natural mass, and mass can serve as shielding. So even a small world can invite larger thoughts about future human presence beyond Earth. Those habitat ideas are still far from practical reality, but they show how asteroids live in both scientific reasoning and human imagination. A small body can be many things at once: a hazard, a fossil of solar system history, a scientific laboratory, a resource target, or a future engineering challenge. This range of roles is part of what makes asteroid science feel so quietly rich. One of the deepest scientific questions is whether the asteroid belt today is made mostly of original survivors from the dawn of the solar system, or mostly of recycled fragments from later collisions. This is a subtle question because the answer shapes how scientists interpret almost every asteroid they study. Is it a direct survivor from the beginning, or a later product of destruction and reassembly? The answer appears to be both. Some asteroids are ancient survivors that preserved a very old identity, while many smaller ones are collisional descendants built from fragments of larger bodies. This mixed picture is elegant in its own way. The asteroid belt is not purely a museum of untouched relics, nor purely a scrapyard of recycled pieces. It is a layered archive containing both. Another major question concerns how much water and organic material asteroids may have delivered to the early Earth. This matters because Earth's ability to support life depended on the presence of key ingredients, and some of those ingredients may have come from beyond Earth itself. Asteroids therefore connect not only to planetary formation, but possibly to the long story of habitability. Carbonaceous asteroids are considered strong candidates for contributing part of Earth's supply of volatiles and prebiotic ingredients. Their dark, primitive material often contains carbon-rich chemistry and signs of past water interaction. That makes them especially important when scientists think about what kinds of matter were available in the young solar system and how those materials may have reached the early Earth. Sampler return missions help test those ideas by allowing scientists to compare asteroid chemistry directly with meteorites and with models of early Earth materials. A controlled return sample is especially valuable because researchers know exactly where it came from and how it was handled. This makes the comparison cleaner and helps turn broad theories about delivery of ingredients into more testable science. Asteroids are also natural laboratories for granular physics because their surfaces are made of grains, pebbles, dust, and boulders behaving in weak gravity. On Earth, similar materials are influenced strongly by air, moisture, and heavy gravity. On asteroids, those familiar influences are mostly absent. This creates a simpler but also stranger environment for understanding how loose material moves. Processes such as angle of repose, particle sorting, and seismic shaking play out differently on asteroids than they do on Earth. A slope that would collapse under Earth gravity might remain stable on the tiny body, while a small vibration could move material farther than expected. These worlds help scientists study how the basic physics of loose grains changes when gravity becomes extremely weak. A small jolt from an impact can redistribute material across much of a tiny asteroid. Because the body is so small and its gravity so gentle, even a modest disturbance can have global consequences. Dust may shift, pebbles may roll, and surface layers may settle into new positions. This means that small events can reshape asteroid surfaces more effectively than intuition from Earth would suggest. Fine grains can migrate into gravitational lows, creating smooth deposits in certain regions. This helps explain why some asteroids show surprisingly calm-looking patches amid rough terrain. Even in weak gravity, loose material still responds to the tiny pull that is present. Over time, grains can collect in depressions or sheltered areas, forming softer-looking landscapes among the boulders. Larger boulders can appear stranded on slopes because the rules of low gravity are not the same as the ones familiar from Earth. A surface that seems unstable by ordinary standards may still hold a large block in place when gravity is weak and friction behaves differently. Asteroid landscapes can therefore look subtly unnatural to us, not because physics is absent, but because the same physics is operating under very different conditions. An asteroid day is simply one full rotation, and on some small bodies that day may last only a few hours. This means the pattern of light and darkness can change much faster than it does on Earth. Quick rotation affects surface temperature swings, thermal stress, and how material responds to the body's spin. Even the rhythm of day and night becomes part of asteroid evolution. Seasonal effects can also occur on asteroids whose spin axes are strongly tilted. Even though these are small, airless bodies, the angle at which sunlight arrives still changes over the course of an orbit. That means some regions may experience long patterns of stronger or weaker illumination, which in turn can affect temperature-driven processes and the slow evolution of the surface. Because sunlight drives thermal forces, an asteroid's spin orientation can subtly influence how its orbit changes over time. The way a body rotates affects where and how it re-radiates absorbed heat, and that tiny asymmetry can produce a long-term push. This is one of the most delicate ideas in asteroid science. Heat leaving a surface can slowly change the path of an entire world. That means two otherwise similar asteroids can drift in opposite directions over millions of years if they rotate in opposite senses. Their sizes and compositions may be alike, yet their long-term orbital evolution can differ just because of spin direction. This makes asteroid history surprisingly sensitive to subtle physical properties. A small difference in rotation can lead to a large difference in destiny. Prograde rotation and retrograde rotation both matter for long-term orbital evolution under the Yarkovsky effect. One direction of spin may slowly move an asteroid outward, while the other can move it inward, depending on the orbital context. Over enough time, this turns spin state into a meaningful driver of where asteroid fragments end up. Motion through the solar system is not only about gravity. It can also depend on how a body turns. Eventually, that slow thermal drift can feed asteroids into resonances that send fragments toward the terrestrial planets. So the path from the main belt to near-Earth space may begin with something almost unbelievably gentle, sunlight warming a small rotating body. Then, over millions of years, gravity takes over and reshapes the orbit more dramatically. It is a graceful chain of cause and effect spread across deep time. In that sense, Earth-crossing asteroids are supplied in part by a very slow conveyor belt operating across the main belt. Fragments are created by collisions, then tiny thermal forces nudge them, and resonances guide them inward. The process is patient and continuous. It does not rush, but over long ages it keeps delivering material from the belt toward the inner solar system. Asteroids preserve memory of both sudden events, like violent collisions, and extremely gradual ones, like thermal drift. This dual nature is part of what makes them so scientifically beautiful. They record explosions, fractures, and breakups, but also the slow influence of heat, spin, and weak gravity. Their histories are written in both sharp impacts and nearly invisible processes. Because of that, asteroids are among the best natural records of how chance and slow physical laws work together in planetary systems. A collision may happen in an instant, but the consequences may unfold over millions of years. A tiny force may act continuously for ages and eventually change the orbit of a fragment completely. Asteroids preserve both kinds of story at once. Modern asteroid science is highly interdisciplinary, bringing together astronomy, geology, chemistry, physics, engineering, and risk analysis. No single field can explain these bodies fully. Their light must be measured, their materials interpreted, their motions calculated, their surfaces explored, and their hazards assessed. That combination of perspectives is one reason the subject has become so rich and active. Each new asteroid discovery adds another data point, but close-up missions reveal that every well-studied asteroid has its own character. One may be metallic, another hydrated, another a loose rubble pile with a moon, another a remnant of a differentiated world. The more closely scientists look, the less these bodies feel like anonymous leftovers, and the more they feel like individual places with distinct pasts. Some asteroids are metallic, some are water-altered, some are monolithic, some are rubble piles, some travel alone, and some are accompanied by moons. This diversity is one of the central truths of asteroid science. The category is broad, but the objects within it are highly varied. Their differences are not small details. They reflect fundamentally different histories of formation, heating, collision, and survival. Some asteroids formed early and stayed mostly intact, while others are the products of repeated destruction and reassembly. This means that to look at the asteroid population as a whole is to look at many different pathways through solar system history. Some bodies are ancient holdovers. Others are descendants of events that happened much later. Together they form a layered and intricate family of small worlds. Far from being insignificant debris, asteroids are archives of solar system history written in rock, metal, dust, and orbit. Their value comes not from size, but from what they preserve. They hold records of formation, migration, collision, chemistry, and time. Each one carries part of a much larger story, and together they help explain how the solar system became what it is. Asteroids show that even the smallest worlds can preserve evidence of how planets begin, change, and sometimes break apart. They are reminders that size alone does not determine importance. A body only a few kilometers wide can still preserve clues to events from the earliest age of planet building. In their quiet way, these small worlds hold very large lessons. And the more closely scientists study asteroids, the more they discover that these bodies are not simple leftovers at all, but diverse and patient worlds with histories of their own. Some remember fire, some remember water, some remember breakage, and some remember long, silent drifting through the dark. And somewhere beyond the steady turning of Earth, they continue their slow paths around the sun, carrying those old stories onward in stillness.